So we will be doing section 6.3 and 6.4, two-section unit, and it's all on vectors. So this first unit is a little bit of like terminology, knowing what a vector is, knowing what a vector can represent, and then by the end of this section, which I don't know if we'll have time to get to today for the notes, we can see some nice real-world questions that are involved. All right, so a vector is when you have like a starting point and an ending point. So in geometry, you would call that array. So we know where you start, we know the direction you're headed, and usually the length of the vector represents something like a speed or a distance. Now normally, we will call the initial point P, and then the ending point, the terminal point Q. So if we know a point, like an XY point, we'll call it P1, P2 from P, and Q gives us Q1, Q2. So then sometimes we have four numbers. Alright, so one of the things that is really helpful is when you can break a vector down into its component form, which means you're breaking it into its horizontal component, how much left and right is it going, and to a vertical component, how much up or down is it going. So this example right here, whatever this represents, I don't care about how far to the right is it moving, that would be the horizontal component, and how much up is it going, that would be its vertical component. So you piece those together, you get what is called component form. Magnitude would be like the length of your vector. And here's the notation for that. It looks like a set of two absolute values. It's not there. And it just depends on what the vector represents. If this vector represents speed of a boat, then your magnitude there would be the speed of the boat. Now, if you have a point, well, one way to find component form, I don't use this a lot, but if you want to know this distance, you can subtract the x values, and if you want to know this distance, you can subtract the y values. For example, if this was at an x location of 2, and this was at an x location of 7, the horizontal component would be 5. 7 minus 2. That's what this is doing right here. Q1 minus Q2. Q1 minus Q1. If the vertical components, if this was 9 and this was 7, the vertical component would be 2, and you can find out by doing 9 minus 7, or Q2 minus P2. Now notice, this kind of looks like a point that has little arrows on it. So the arrows is how we know that it's talking about a vector and not a point. Do parentheses, you assume that it's talking about a point. Right, well, if you've got 2 points, you could plug them into this formula, and that would give you the magnitude. Does anyone recognize this formula? It's a distance formula, right? Hopefully you know that for ACT. But if you have 2 points, the distance between 2 points is the same thing as that length, and the length would be the magnitude of the vector. So that's one way that we could do that. But notice my picture here, horizontal component and vertical component are always going to be perpendicular. So you're also going to have the right triangle, and you can instead do Pythagorean theorem if you want to. Okay, so let's actually make up some numbers and try this out. Alright, sketch a vector that starts here and ends there. Starting point P. Ending point Q. Put the arrow on it so that you can see the direction. Vectors do care about direction. So that's what number 1 is describing. Okay, question 2 wants us to break this up into component form. So again, this is a vector, so we're going to use these little arrows. And like instead of an x value, this is going to represent the horizontal component. So how much left or right is it going? And instead of like a y value, we have a vertical component, which is like saying how much up or down it's going. So the formula above says that, so this is like ray PQ, you could take Q1 minus P1, comma, Q2 minus P2, and the vertical. And then 3 minus a negative 1 is 4, 5 minus a negative 1 is 6. Now, whether these are positive or negative makes a big deal. Positive 4 means it's going right 4. Positive 6 means it's going up 6. Those are negative, it would be left and down. Now, when you have a picture, this is kind of silly to do this formula. So, I honestly almost never use this one, but I still think it's important. If you have a picture, or you can make a picture, and you know where it starts and you know where it ends, you can count that it goes to the right, 1, 2, 3, 4. And you can count that it goes up 1, 2, 3, 4, 5, 6. And that's what component form is trying to represent. Good way to generalize where it's going. Okay, and then if we wanted to know the magnitude of the vector, so in other words the length of the vector, we could find the distance between those 2 points with the, so this means magnitude, with essentially the distance formula. And we would subtract P1 from P1, square it, subtract those and square it, so 4 squared would be 16. And then Q2 minus P2, Q2 minus P2, square that, so it would be 6 squared, it would be 36. Square root of 52, which is 2 squared 13 maybe. And you can do that, and I'll be honest, I don't use this formula very much. And it's good for you to know. If you have your picture, what's another way to find the length of that? Right, because these are forced to be perpendicular. Horizontal lines and vertical lines have to be perpendicular. So, most of the time, I say it makes more sense to say a squared plus b squared equals c squared, 4 squared plus c squared is 6 squared c squared. So c would be the square root of 16 plus 36. You see how your work ends up being the same anyway. Distance formula is just a variation of everything. About 99% of the time I can get this to everything. 99% of the time, component form, I just calculate, I count out how much left to right is going, how much up and down is going. But there's the formulas built into it. Okay, I want you to practice this. So different vector, and then try writing out the component form like I did in question 2, and then try to find the magnitude like I did in question 3. So you try it and see what you understood and what you didn't understand.
So there's what our vector should look like. Notice my arrow. You really want to put the arrow in there. Even if you label in pink, you just put the arrow there. Alright, so component form is a way for us to determine how much left to right is going and how much up or down it's going. So don't use parentheses. That would mean a point or something else. Use little arrows. And feel free to use that formula to do that, or you would subtract the y values and subtract the x values, or sorry, subtract the x values and subtract the y values. It's for horizontal component. But with the picture, hopefully you can see, you get from 8 to -2, how much are you traveling here? Okay. You're traveling 10, and you're going to the left. And then we get from 2 down to -5, you're going down 7. So the formula is fine, just usually you can just make sense of it. Alright, and then same thing with part 6. You can use these 2 points in the distance formula. The distance between the 2 points is the same thing as the length of that line, which ends up being the magnitude of the vector. But you've got the whole picture set up here. You can see your right triangle here. So there's nothing wrong with Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. So the square root of 147. No? So, it's almost mostly vocabulary here. Knowing what magnitude means, knowing what component form looks like, and what it means. Like, it's not that it's difficult, though. Let's move forward to the next page and talk about something else. So all this does come together at the end. There is some nice real-world applications that you can solve with this, but you can't solve with other subjects. But before we can get to that, you also need to know that you can do arithmetic operations or arithmetic operations with vectors. So if this is V and this is W, what do you think 2V means? Just multiply by 2. Works just like you would expect. If it says W minus V, you should subtract the horizontal components. So 3 minus -2. Positive 5. And then subtract the vertical components. 4 minus 5. So multiplying by 2 looks like this. Multiplying by half is the same as dividing by 2. So let's divide W by 2. So that means the horizontal component gets divided by 2, and the vertical component gets divided by 2. Sometimes you have fractions, sometimes you don't. And occasionally you need to do a couple steps here. Maybe take 2 times W, which would be that, plus B, which is this. So you see I already doubled W, and then adding those. Add the horizontal components, get your horizontal component. Add your vertical components, add your vertical. 2 times W, so that would be negative 6 and 16. But nothing tricky really going on there, just gotta be careful with what we're doing. Alright, and let's try to squeeze in maybe one more idea here. So, to manipulate vectors and to make it where we can use them, we often want to change a vector into what we call a unit vector. A unit vector means it has a magnitude of 1. So sometimes we like to take a vector, maybe it has a length of 5, we'll change it to a unit vector so that it has a length of 1, and then we can easily manipulate it and make it have a magnitude of 100 if we want to. But we always want to change it to a unit vector first, magnitude of 1. Okay, so to do that, let's break this up into a couple of steps and then have you practice it. You would want, if I wanted to change this into a unit vector, I would first need to know what its magnitude was. So, sketch it is going left 3, and up 4. Now notice, I don't have a point, so I don't know when this is occurring, but it doesn't really matter. I know it's going left 3 and up 4, so that's what my vector looks like. So what does that mean about the magnitude? Okay, 3 in triple. Negative 3 squared plus 4 squared will give us 5. Alright, so as it stands, this vector has a magnitude of 5. How do you think we can change it to get it to be a magnitude of 1? Okay, 5 times the magnitude, in this case divide by 5. It's going to make it 5 times smaller, which is going to make it length of 1. Okay, so take our vector, divide it by its magnitude, and multiply it by a fifth. And then there's its unit vector. Now the great thing about this, and why this is so useful, is that this vector is still in the same direction as this vector, still pointing the exact same way. It's just that you're literally shrinking it down to a length of 1. So, given that we have that same vector, and another vector that's in the same direction that has a length of 7. Alright, so this vector has a length of 5. Make sure you're paying attention here. This is very quick. This has a length of 5. I want to find another vector in the exact same direction that has a length of 7. Okay, well, do I know a vector that's in the same direction that has a length of 1? That's unit vector. How do you think I can make it go from having a length of 1 to a length of 7? How about 7? So 7 times its unit vector is going to force it to have a magnitude of 7. And it keeps it in the exact same direction. It doesn't go slightly up more, slightly to the left more, it's still in the exact same direction. Okay, so last question we'll look at, and then that's for today. we want to find another. So this is how it's usually phrased to you. The last like 4 questions is just from inching towards that. Usually it's going to say find another vector as in the direction of this vector, but one that has a length of 12. Well, what is this thing? Does this have a magnitude of 1? Because if it does, I can just multiply it by 12. It doesn't, unfortunately. But I could quickly draw a picture. This is like saying it's traveling right 5, down 2. Quick visual of what it looks like. With diagram there, I can tell you its magnitude is currently the square root of 29. So if this guy is d, and the magnitude of d is the square root of 29. So how can I change it from having a magnitude of square root of 29 to having a magnitude of 1? Okay. Divide by the square root of 29. Divide by the square root of 29. Technically that does have a length of 1 now. And it doesn't change the direction. More important. So this guy would look like this. Alright, but you know that we're probably going to rationalize this. The top and the bottom by the square root of 29. At the top and the bottom by the square root of 29. So this has a fancy name, and we will ask you to find the unit vector multiple times. So that was the question that will be done. But more importantly, you understand that this means that the magnitude is 1. Unit, singular. But now that I have a magnitude of 1, all I have to do is if I want it to be magnitude 25, multiply by 25. If I want to have a magnitude of pi, multiply by pi. In this case, I want to have magnitude 12, so multiply the whole thing by 12. Which we saw from the arithmetic at the top of the page. Just means the horizontal component gets multiplied by 12, and the vertical component gets multiplied by 12. Of course, we can always look at the decimals on that when we get to that. But I know for sure it's in the same direction as that vector, and I know that it has a length of 12. Not something you could just jump to, but if you can manipulate it to have a length of 1 by dividing by its magnitude, and anywhere to a magnitude of 12, multiply it by 12, then you have dealt with everything that you need to. Alright, so for today, we are going to stop there.